What do you see on number 5 right here? What is that? It's the difference of something. Yeah, so that's going to be 2 over s squared minus 1 times s squared plus 1. So when you factor this, it's going to end up being s plus 1 times s minus 1 times what? S squared plus 1, exactly. So can you factor that any further? No. So is this single power non-repeating terms? No. There is one thing there that's a little higher. Just because it's not on the AP exam doesn't mean you can't figure it out. If you wanted to write this out, you're going to need to write it out as a over s plus 1 plus what? Yeah, you have to be careful here. B over s minus 1 plus what? Cx plus d over s squared plus 1. Now this one's a little bit more complicated, but you're not actually doing the integration, so we might as well do it here. So if you do this out, you multiply by all those denominators. So what do you end up with? 2 is equal to a times s minus 1 times s squared plus 1 plus b times s plus 1 times s squared plus 1 plus cx plus d times what? Yeah, a lot of s's in this one. I don't like s. Sorry, my s's don't look very good. So what was that? Did I show you that like magic number method? Yeah, so you pick magic numbers. Just do it on this one. It's a lot easier. So what's a nice first s value to pick?
1.
Yeah, s equals 1. If you pick s equals 1, you end up with 2. What happens to that first term? Gone, right? And then you end up with b times 2 times 2. And then the last one is 0. So what does that tell you? B is equal to 1/2. So then you pick s is equal to, let's say, negative 1. Is that an okay thing to pick? Yeah, if that's equal to negative 1, you end up with 2 is equal to a times negative 2 times 2. And then the second term goes away and the third term goes away, right? So what does that tell you a is? Negative 1/2. So we have a and b. Okay, now are there any other magic values that you can use? Not really. I mean, you could, you could. No, seriously, you could put an I, right? But then what's the? Do you want to try putting an I and see what happens? No. Why not? Let's try it. I can say I've never had someone propose that before. I think it's a great idea. Let's try it. No. I see why you're doing it, Ali. Let's see if it works out. So let's set s equal to. Yeah, my cursor's now going berserk. So in any moment this is going to freeze up. I know. I think it might actually work. So let's take s equal I. If we do that's the case, what happens to the first two terms? The first blocks go away, and you're left with cx plus d, which is I plus 1 times what? So what do you need to? What is that? This is kind of cool. I don't know. This is the first time. Nice. Equals cx. But what is x? It's I. Is that a good thing? All the x's. All the s's. I'm sorry. You're absolutely right. I'm sorry. Excuse me. S and x. I gotta. Right. So you end up with what? Negative 1 minus I plus I minus 1, like that. So do the i's go away right there? Okay, that's kind of cool. So you end up with 2 is equal to cx plus d times what? Negative 2. Now, we need to find c and d. Actually just need to do it out, yeah. So if you actually just do this one out, you end up with 2, sorry this is being annoying, 2 is equal to what? Negative 2cx minus 2d. Are there any x's on the left side? So what does c have to be? C has got to be 0, so what does that make d? All done. Awesome job, Ali. I like that idea. Plug in negative 1 for that. Very cool. I like that. I mean, what was our hesitation for doing that in the first place? Like, why were we hesitant? Why didn't we want to do that in the first place? Well, no, we didn't want to use I, but why didn't we want to use I? We thought it might be messy. We might think I would remain, and you're like, oh, we can't have an imaginary, but guess what? It went away. Very cool. Very, very cool. Okay, so let's try it. w equals x squared plus 10. So what does that mean? dw equals 2x. Oh, that's a. I'm sorry. Thank you very much. Thank you. Oh, yeah, that would make a lot more sense. The square root of 10 tan theta. Oh, come on. You know this one. You can do it. You got it. Okay. So if you do this, what does dx equal? Square root of 10 times what? Derivative of tangent is what? Secant squared theta d theta. Correct? We good? So if you do this, so the question is why. You want to know why. Why does this work? What do you end up with? 1 over the square root of x squared. Sorry, excuse me. I didn't put it in the right place. You end up with 10 tangent squared what? Theta plus 10, right? This extends over here. And then instead of dx, what do you have? Well, the square root of 10 secant squared theta d theta, correct? Yeah? We did this substitution right here. When you do the derivative, the constant stays. You know that. You do know that. Okay. Why does this work? What can you quote unquote like factor out of the square root on the bottom? So well, it's going to be root 10, right? So what are you going to end up with? The square root of tangent squared plus what? 1. And then what do you have on top here? The square root of 10 secant squared theta, and you have d theta. What can you do with that square root of 10? You can cancel it with the one on the outside. So what are you left with? Secant squared theta over the square root of tangent squared theta plus 1 d theta. Anybody remember what tangent squared theta plus 1 is? Yeah. It is secant squared. It is secant squared. That's why. Because when you do this substitution, you end up with secant squared theta over the square root of secant squared. So what is it? Secant, not squared, right? Just secant theta d theta. Does that simplify? Secant theta d theta. That's why you get to something that you can integrate. So it's kind of like reverse planning. You're trying to build something that gets you to a trig identity that collapses that square root. That's why. The Pythagorean trig identities, you know that cosine squared plus sine squared is equal to? Yeah, you divide by cosine squared and you get 1 plus secant squared over cosine squared equals 1 over cosine squared. Divide by sine and what do you get? Cosine squared over sine squared plus 1 is equal to 1 over sine squared. Well, sine over cosine squared is tan squared. So I'm just doing the shorthand of this. So you have 1 plus tan squared equals, what's 1 over cosine? Secant squared, right? And this you get cotangent squared plus 1 is equal to cosecant squared. So if you ever need to do the shorthand way, that's the shorthand way right there. Okay, anything else from the actually? So if you're going to do x cubed plus 12x squared plus 11x, if you were going to do this division, now it's a lot to write down, but it doesn't go very long. Why isn't this a long process? Yeah, the difference in the powers is very minimal, right? Do you remember how to do polynomial long division? You do leading over leading. What's the leading term in the radicand underneath the division? It's x to the 4th. So you do x to the 4th over x cubed. The only thing you need to remember for long division is leading over leading. So that's from here, and the x to the 4th is the leading term initially right here. What's x to the 4th over x cubed? It's x. And then what do you do? This is just like long division. What do you do with the x? You multiply it. What do you get? X to the 4th plus? Oh, is this kind of nice? It's not bad. Plus what? And then there's plus 0. Right? There's zeros here. What do you do here? You subtract. And now a nice thing happens. If you did your division correctly, this should go away. Hey, did we get another one? Did another one go away? What went away? That went away. And what are you left with down here? 4x squared plus 25x plus 11. You bring those down, right? Now, do you go any further? Do you go any further? No, you don't. So what does this now tell us? This tells us that this is equal to the integral of x plus 4x squared plus 25x plus 11 all over what? Cubed plus 12x squared plus 11x. So all the division allowed us to do, Tina, is rewrite it. This is the remainder, right? This is the remainder. Because this power is less than that power right here. You stop, okay? So this is the remainder. Everybody remember long division, you get to the remainder? So this fraction right here is the same as x plus the remainder over the original, right? Now, why did we do that? We did that because what can you do when you have the sum, when you're doing the integral of the sum of two things? What can you do? You can break them into two, right? So now it really comes down to, Tina, now you're just doing the integral of just. Sorry, that was not a good word choice. Over this. And this right here is something you can do because they gave you the factorization of the denominator, right? Didn't they factor it for you? Wasn't that really nice of them? So you now know that this is going to be equal to the integral of a over what's the first one? It's just x, right? A over x plus b over what? X plus 1 plus c over plus what? Is it c? I can't remember. What does it say? Oh, c over x plus 11. Hey, it's linear term still. Nice. Okay, so this c over x plus 11. Nice. Like that. Now, how do you set this up? You do the same thing you did before. You multiply and you go. But that's what it meant. You get to shave off part of it. You get to shave off part of the numerator because do you really want to set up a simultaneous equation with that numerator? I don't really want to do it. The x? Oh, that's just separately. That, like, ready? Yes, I am. Plus, there. Got it? So, ready? X plus that. Okay? So that's what it's asking you to do. As far as I know, even though this right here is linear terms, I don't think you need to do I've never seen the question require you to do polynomial long division inside a partial fraction decomposition on the BC calculus exam. We might find it. We're going to do a ton of practice problems. I have never seen one. I think it's highly unlikely that you would time. T represents time. And the idea is you have an index variable that's going into a function that dictates the x and y coordinate. Are there accidents very often on the road outside compared to the number of cars that drive on the road? Not really, right? Why is that? Because the same two different cars don't occupy the same space at the same time. You can use parametric equations to describe motion. You can use parametric equations to describe motion because you have a path. It gives you a path, but it also gives you where you are at each individual time index. So at time equals 0, where are you? At time equals 1, where are you? So you can travel along a parabola. How many different ways could you travel along that parabola? An infinite number of ways. An infinite number of ways. Okay, so for example, let's say I asked you this, and we're just going to do this as a group right now. Describe the motion of a particle whose coordinates at time t are x equals cosine t and y equals sine t. So yeah, you're going to get good enough to be able to look at these and be like, oh, I know what that looks like. But let's say you didn't do that. What's the best thing you can do if you, on any graph that you're trying to make, what can you always go back to making? No, like before you make the graph, what are you plotting on a graph? Intercepts. Points, and to like what's a great, intercepts if you can, sure, absolutely, intercepts are great. We could make a table, t, x, y. Now, is it important that we choose t values that are kind of helpful and not counterproductive? Sure. So how about 0? Is 0 an okay value to choose? Yeah, because what's cosine of 0? 1. What's sine of 0? 0. And then what kinds of values should we choose for t on this? Values that nicely come, pi over what? How about pi over 4? What's cosine of pi over 4? Is it root 2 over 2, right? And then what's sine of pi over 4? Root 2 over 2. And then pi over 2. What's cosine of pi over 2? 0 and then 1. And then what's the next value on this going to be? 3 pi over 4, right? So what's cosine going to be? Negative root 2 over 2 and root 2 over 2 and then pi. What's that going to be? Negative 1 and 0. So we can keep on going, but let's graph those points and see if it actually tells us something. Let's see if it tells us something. Ah, some kind of circle, right? So it starts at 1, 0. Then it goes, well, let's make it right here actually, and then it goes up to root 2 over 2, and then it goes to there, and then it goes to there, and then it goes to there. This is not the best arc I've ever drawn in my life, but it looks like at time 0 it's right there, then there, 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 and there. What do you think it's going to continue doing? And then eventually, is it going to overlap itself?
Yeah.
Absolutely. Yeah, you did petals and cardioids and did really cool. Are they? Wow, that was great. I get this right vision right here. I get Fiona Vista smiling and going like this, and the camera going. Like, same head motions. Like, plotting points more often than you're probably going to, because you're going to think to yourself, oh man, I should just know what this shape is. I should know what kind of limacon it is, and no, make a table, okay? Make a table. It's really important, because one of the easiest ways to get polar questions wrong in the BC exam is making simple mistakes. So for example, will you be integrating later? Will you be integrating polar equations? Yeah, you will be. And it's actually not that bad, because instead of adding together lots of rectangles, you're going to add together lots of triangles. It's really not that different, right? But here's the thing. That parametric equation, does it start overlapping itself? Yeah, it just sits there running on that circle the whole time. So what happens if your limits of integration are too big? Like you go from 0 and then it's going to get all the way back to 2 pi, right? What happens if you integrate it from like 0 to 4 pi? You'd have to divide by, if you wanted just the area, you're going to overlap twice is what I'm saying. It's really easy to over-integrate with polar. Really easy. It's super easy. Okay, now, could I, instead of giving you a function, could I give you effectively the graph of each x and y with respect to t? Absolutely. In this case, if you wanted to graph the actual path of this particle, you need to make a table. To graph this particle's path, you need to make a table. So we have t, x, and y. So when t is 0, what's x? Look at the graph, and what is it? 0. What's y? No, it's 0. What is it? 0. At 1, what's x? 1. What's y? 0. See what I mean? At time equals 2, what's x? 1. And at 2, what is it? 1. And at 3, what is it? 0 and 1. And then at 4, it's at 0 and 0. So then what do you literally do? What are the points here? You have 0, 0, and then 1, 0, and then 1, 1, and then 0, 1, and then 0, 0. So what does this look like? You start at 0, 0, and then you go to 1, 0, and then you go up to 1, 1, and then you go to 0, 1, and then you go down to 0, 0. That's kind of cool. So there's a parametric like bifurcation of a box. You've pulled it apart, it became a box. Now, can you do certain things to make these shapes very similar, but the behavior of the particle on the path different? Yeah. This one right here. Anybody want to guess what does this look like when you graph it? What does the path look like on this one, do you think? It's a circle still. It's still a circle. It's cosine and sine, right? Is it the same as, it's the same overall functions we used before, right? What's the only thing that's going to change? No, it's not actually, no. It's going to, if you graph this and just looked at the path itself would be exactly the same. The what of the particle? Yeah, if you say the speed of the particle changes. Because look, when we had cosine, if it was just cosine of t, you plug in cosine of pi over 4, right? But instead now, not cosine pi over 12 is going to act like cosine pi over 4. This particle will travel along the same path, but this car is driving faster. So if you just looked at the path, it's going to go around. It's going to start here and go like this, right? But how much faster does this one go? How long, what time does it go all the way around? We knew it was 0. It started here and went all the way around, right? And it got back in 2 pi. How long does it take for this one to go all the way around? 2 pi over 3. It's 3 times faster. It's 3 times faster. So it's on the same track. It's going 3 times faster. Does that kind of make sense? You could do that out by just listing out points. So instead of listing pi over 4, you would list like 0, and then pi over 12, and then pi over 6. Sorry, pi over 8. 12, and then 8, and then 4. And that would get you the same path.